Okay, so today we're going to do a real neat application. Just let me go back one here to kind of show you. We finished how free energy relates to equilibrium, and now we're going to talk about electricity and a flow of electricity, and that's going to get into oxidation reduction chemistry. You can see we have two units left here. And they're both pretty intense, so we're going to be breaking it up into two chunks. So we'll start this 9-7, and then we'll call the next one 9-9. We'll be starting that one on Wednesday. So 2 days on this and 2 days on this, with some other miscellaneous things thrown in there. Okay, so and that'd be kind of, you know, like test prep and things along those lines. All right, so let's go ahead and take a look at this 9-7, 9-8 with producing electricity and how that can be done through the wonderful world of chemistry. Okay, this very first slide here talks about a reaction of if you just took a piece of zinc and put it into this blue solution, which is oftentimes the case with a copper solution. Sometimes they'll ask a multiple choice question about that. You know, what color solution would copper +2 make? And so it'd be this bluish solution. What's going to happen is the zinc will actually start to disappear. Okay, and it does that by exchanging and becoming zinc +2. So you have these copper ions out here, which have lost 2 electrons. So so they are in essence, looking to get those electrons back, and then because of the activity series, the zinc is willing to react with the copper. If you did this in reverse, put a piece of copper in a zinc sulfate solution, nothing would happen. But here, the zinc is actually going to start to disappear. And what'll happen is that these copper ions will start to form on the surface, and it'll actually kind of get fuzzy over time. If you're in class, we're going to show a little demonstration of how that happens as these copper ions start to form on the solution. But you can just rinse that off. They're not part of the structure as much as this diagram shows you. You just rinse off that extra copper, and you can see that the zinc will lose its some of its mass. Okay, so so you see now we have the zinc +2 ions because it gave up 2 of its electrons. All right, so that's at the core of what's going on here, and essentially what you're doing is you're saying this one thing wants electrons more than this thing, so therefore they're willing to exchange that. So now we're going to talk about how you write a balanced redox reaction. So you see anytime a solid metal is placed in a solution containing metal ions, that's the type of reaction that you're going to be talking about. So for instance, a copper penny is dropped into a solution of silver fluoride. Okay, we're going to do silver nitrate for the students in class, and you'll see that the penny will get all covered in silver. But the reaction is you have the copper and the silver ion. The silver ion is always going to be a +1. Whenever we're dealing with copper, by far the most common form is copper +2 ion. There is a copper +1 ion, but that's not the the one that's going to form in these reactions. And then you'll have some solid silver. So it's like the penny almost looks like it gets like a little silver hair on it. It's pretty interesting. So you got to balance the charges in the reaction, and to do that you needed that extra plus charge on this side. You certainly didn't need to balance the AGs. They were already, and you're putting a 2 in front of both of them. So that's the little trick to doing these, is to remember you got to balance the charges as well. Okay. Now, what is a galvanic cell or voltaic cell? Is the preferred way of talking about that, or at least certainly that's what I prefer, is to call that a voltaic cell. And the delta G is less than 0, so that means that when you make these things, they're going to give off electricity. So you don't have to plug them in. If delta G was greater than 0, it would be non-spontaneous. It would not be thermodynamically favored. So you would have to plug it in. And we're going to talk about those coming up. But this one, it just happens. It's a thermodynamically favored process. As a matter of fact, the discovery of a battery using metals to make a battery was a serendipitous discovery by Galvani, who was, many scientists at the time did a lot of things, and he worked with animals, he worked with plants, he worked, with chemistry and physics. They were a much broader, not specialized like you see today. But he was working with electricity, so he was fully understood, how you make that and what electricity is. But he was also doing some dissections, and the story was that he was, and he actually, this is true, it's not just urban legend kind of thing. He was using 2 different metals to dissect a frog. Now the frog was dead, but when he touched the 2 metals, that little frog leg went me 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 me, and he was like, I've created life. And at that time, what's very interesting, a certain author by the name of Mary Shelley came up with a story about Frankenstein, Dr. Frankenstein, who was trying to reanimate living tissue, because they thought that's what was happening. And in reality, after they looked at it, and Volta, who was an Italian scientist as well, said, well, we gotta look at the science behind this thing and kind of talk about, and he saw that, look, we have this source of electricity, and when we touch that to the frog leg, the same thing happens. So what occurred was 2 metals were used to make electricity, and that was just spontaneous. And that is the story behind the beginning of the battery. Very interesting. But chemical energy was converted into electric energy, and we have a great deal of appreciation for this right now. Your phone is being charged by a similar process that was making that frog leg twitch. Okay, so this is definitely circle this diagram right here. If you could understand this, it's really, really going to be helpful moving forward. But this is the classic voltaic cell, classic way of making a battery. So the things that you'll want to emphasize is the direction of these arrows right here. Circle that arrow, because the movement is, the solid zinc is moving away here, and then this guy, you're going to find is actually going to increase in mass because the arrow is going toward it. Now, in terms of the electrons, this is another point of emphasis. Star this or highlight this. The electrons are coming out of the anode. Okay? They're coming out of the anode. And the reason is this is the reaction. Zinc will give you zinc plus 2 and 2 electrons. So at the very top of this thing, out come electrons. It's just puking electrons out. See how the electrons are a product? That is what produces electrons in this reaction. And then over here, you want to get electrons. This is called the cathode. Okay? This is called the cathode, and the electrons are moving toward the cathode and into the cathode. So when you get that flow moving, that's what causes this. I think that's a light bulb right there. Something sort of looks like a light bulb, maybe a pear, but I think it must be a light bulb. So you're some sort of source of electricity, and in this guy goes through the copper, and then the electrons move this way because this is the negative part, so the sulfate ions come right through there and go through there, and this is what we call a circuit in the physics world. Okay, that's a circuit that has been created. Those plus ions can drive up and come this way, replacing the positive ions that are being turned into copper over here. So what's really important is that you remember this is the oxidation side, and this is the reduction side. And you remember that Leo, loss of electrons, is oxidation. So write that on this slide. Write Leo right over there, and over on this side, write Ger. You're gaining electrons. That's reduction. Yeah, look at everything about this. You're gaining electrons. You're gaining electrons when you look at the half reaction. Ger. You're losing electrons. Reaction. I don't know what I was trying to say there. You're losing electrons over here at the anode. Okay, so you're going to want to find a way to remember this. A way of. I always remember a red cat. That helps me. A red cat. So reduction occurs at the cathode. And then this is weird, but there's an ox named Anne, which I think is a really cool name for a great big ox. You know, you just go, hi Anne, the ox. So Anne the ox. Anode is oxidation. Cathode is reduction. And certainly if they have a question like this, they're going to assume that you know this. But if you use this, and then hopefully you've already have at least one circle or two stars, explanation points, everything necessary to emphasize the importance of this diagram right here. Okay, so this is kind of a cool diagram that shows shows you what's happening with the individual, as if they were like a little cluster of atoms, which is what they are. The zinc is getting smaller. We have these old pieces of zinc that we used in batteries that have holes in them, because over time the zinc just leaves. So the solid ones are leaving to become ions. Here are the ions, and then this one actually gets kind of thicker and heavier as it goes through. And then this shows you your flow of electrons as well. All right. So nice little explanation at a little closer look at the atomic level there. All right. So we'll stop this video right here and continue our discussion about making electricity to make frog legs move.